Okay, so this is the electricity topic for P1, and some of you have said you'd prefer the video as it's easier to work through while you're making your mind maps. So in terms of your mind maps, I would expect that you know what a switch looks like, open and closed. So I don't think you need to include those. So as you go through these, the circuit symbols for electric circuits, if you remember that this is a cell and that the small side here is the negative side, that might be worth adding if you didn't know that, but not if you do. I would suggest that the symbols that are easier to forget and might want to be on your mind map are the diode, which makes electricity flow in one direction only, and the arrow shows that. A rectangle is a resistor, and then an arrow through it means it's a variable resistor. At the same time, this symbol is a thermistor, so again a rectangle, so it's a type of resistor, but it depends upon temperature. And then this one, again, it's a rectangle down here, but it's a light dependent resistor. Ammeter's fairly easy, voltmeter's fairly easy. The fuse just has a rectangle with a wire going through the middle, and most people will recall what the lamp looks like. In terms of reading questions about electricity and all these words that are used like current, potential, difference, resistance, it's important that you know in your own terms what that means in your mind. So if you're trying to simplify this, the current is the flow of charge, which means the current is the little electrons that are negatively charged flowing through a circuit. The potential difference is measured in volts, so a lot of people refer to this as the voltage. And you'll see on a 12 volt battery that means a potential difference of 12 volts. The voltage is what gives that electron the push to make it flow. So the voltage, the potential difference, causes the electrons to flow. Therefore, if you have a bigger potential difference, you have a bigger current. Charge is the amount of electrons flowing around a circuit. So if we have lots of electrons flowing around a circuit, there's a bigger charge. Resistance is anything that works against the flow. So some metals are harder to flow through. Some materials that are non-metals are very hard to flow through. So we say they have a very high resistance. They're working against the electricity. A series circuit, that's where the electricity leaves, goes round, might go through some things and then goes back. It's just got one path to go, round and round that circuit. Whereas a parallel circuit might have several branches off it. So the electricity might go down this branch or this branch before going back to the power supply. Okay, the first equation, and remember you're given all these equations on an equation sheet, is the charge. That, remember, that's how much is flowing, how many electrons. That is the current times the time. So when we work out how many electrons have actually flowed, how many are flowing all the time? How long were they flowing for? So Q equals I times T. Now this C is the unit coulombs. Current is measured in amps and time in seconds. So just important that you always convert into those. Especially when they give you minutes, you remember it's always in seconds. If they give you milliamps, you times by 1,000. If they gave you kiloamps, you divide by 1,000. Here's an example question. A current of 1.2 amps flowing for 5 minutes. First thing I think of is Q equals I times T. So the number of coulombs is the current. Right, I check the current. Yes, it's 1.2 amps. I don't need to do anything with it. Here it is. Then I check the time. The time is 5 minutes, but I know it has to be in seconds. So 5 times 60 is 300 seconds. Therefore, 1.2 times 300, 360 coulombs. Second equation, the potential difference, the voltage, is equals to the current times the resistance. V equals IR. This also can be rearranged, so make sure that on your mind map you're probably best off recording these equations in triangles. V at the top because it's equal to I times R, and what that means is, of course, you can now get the equation for resistance, for voltage, for potential difference, or for current. Only thing really else to mention on there is the fact that resistance is measured in ohms, where I've just indicated there with a highlighter, and it has the symbol, the ohm, omega. An example, they show you quite a complicated circuit. You know the electricity is flowing around, off it goes, through the ammeter. Now look where the ammeter is positioned. The ammeter is in the circuit because it's measuring the flow. So I'm just going to write that on there. The ammeter, oh no, I'm not going to highlight in purple, I'm going to use my pen. That ammeter is in series in the circuit. Series as it's in the path of the electricity. That means the electricity has to flow through it because the current is the flow, and that's what it's measuring. And that's 0.2 amps. Remember, it's asking us to work out the resistance of this object here. So, the voltmeter is telling me the difference between here and here, the potential difference is 9.4 volts. Now to work out, you know your equation, V equals I times R, it's on the equation sheet. We put that in our triangle, V, I, R. That means resistance is equal to V divided by I. So as soon as I've rearranged my equation, I can now put in my 9.4 volts divided by 0.2 amps, and I get 47 ohms. And I get it right. Looks like there's a lot of writing, but remember, we're doing a mind map, we're doing just little pictures. So I've sketched out my potential difference against current, and what normally happens is as you push more, remember the potential difference is the push, the voltage, as you push more flows. That relationship where it is a straight line is called directly proportional, and it's written there. Whoa, just highlighting there rather sloppily. If you push in the other direction, so you turn your battery around, the electricity flows in the other direction, and as I said, directly proportional. Here what happens in a lamp or a light bulb is it starts off the same. Starts off that the higher the voltage, the higher the potential, the higher the current, and it starts off the same in the other direction. But what happens then is because the wire starts to heat up here, because in a bulb it's giving off lots of heat as well, as the temperature increases, it makes the resistance increase, and that's because the particles are vibrating more and therefore getting in the way of the electricity. So now I carry on increasing my potential difference. The current increases, but not by as much, and that's why it goes from starting off steep, then the resistance is higher, so it doesn't increase as much and as much and as much, and when you draw all those together you get that smooth curve. And at this point up here where I've just finished off that red line, you can keep increasing the potential difference, but no more current can flow through. And then this one is a diode, and the purpose of a diode is to make sure the current flows in one direction. So when I push in this direction, the current flows lovely. Hey! When I push in that direction, the current hardly flows at all. And then the two types of resistors. If you remember back on the first slide, I'm just looking at the time, back on the first slide 10 minutes ago, we've got, just change pen, we had the thermistor, this one, and that's where the resistance is affected by temperature. And if you look here, as the temperature increases, the resistance goes down. Same with this one, a light dependent resistor. As the light level increases, the resistance goes down. And that, remember, is the symbol I said to draw at the start, because people forget it, the thermistor. That's the symbol for the light dependent resistor. So in terms of measuring resistance, you need an ammeter in series, and then this is whatever, this could be a motor, this could be anything, so I'm just drawing question marks. To measure the resistance of it, I need to get R equals V over I from my equation, the same one we've used already, V equals IR. So the resistance is equal to the voltage divided by the current. So all I need to make sure is I've collected the current in series and the voltmeter is attached in parallel. Because it's measuring the potential difference between that point there I've just drawn and that point there. In a series circuit, the electricity, remember that's the positive side, the little side is the negative. The electricity goes along here. Actually, I'll swap to my highlighter and flow it along. So here goes the electricity, and then it goes through here. Now the bulb gives some resistance. And in a series circuit, when it goes through the second bulb, there's more resistance. And the third one, more resistance. So now those bulbs would be quite dim because there's a lot of resistance. And back around it goes. So that means the potential difference, the voltage of the battery, is shared. The current's the same everywhere, and to get the resistance, you just add them up. So that might be R1, R2, R3. To get the resistance of the circuit, you add the 3 up. In a parallel circuit, the voltage, the potential difference up here, where I've just highlighted yellow, let's say for example that was 5 volts. That bulb would get 5, that bulb would get 5, that bulb will get 5. They've all got their own connection to the battery. So if I go back to my highlighter, I'm starting again. There's the current flowing out of the battery here, and then some of the current flows through that bulb and back. It doesn't know about the other two circuits, it doesn't care about them. More electricity flows through this one, where I've just highlighted, and more electricity flows through that one, where I've just highlighted, and back to the battery. That means when you add together, 6 amps flows through this part of the circuit, 6 amp flows through here, 6 amp flows through here. That's why it says here there's 18 amps flowing. Electricity can do two things. It can do alternating or direct. Where's your examples of that? Your examples are when you have something running off a battery, it's running off direct current. This graph here. If you have a 9-volt battery, here would be your 9 volts. The electricity flows in one direction and it stays in that direction all the time. That's just typical of what we've just been drawing. So here we have a bulb in a circuit and direct current from the battery. It flows, got to swap again. It flows around here, through there, and round and round and round again, and round and round and round again. Direct current. In reality, mains electricity, that's what comes out of the plug sockets, is over here. It's an alternating current. So actually what happens is the live wire, so mains electricity is alternating. What actually happens to an electron try and get that fixed in your head. Here's an electron, and what actually happens to it is it moves that way, and then 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 it moves that way. So electricity is flowing, but it's flowing back and forth, back and forth, back and forth, back and forth. And that's why the potential difference is negative, then it's positive, then it's negative, then it's positive. And our electricity is set to 200, I mean this one on the graph shows 300 volts. Ours is set in this country to 230 volts for a potential difference. And it alternates 50 hertz. We did hertz with light waves and sound waves. 50 hertz means it's alternating up and down 50 times a second. So if I'd looked ahead, I'd have gone for the fact that 230 volts, now I'm messing up my highlighters, 230 volts, 50 hertz. You are expected to be able to label the parts of a plug and what they do. So, the live wire inside a plug is brown in colour, and that is the one that alternates between being positive and negative. The neutral wire works with it. Whichever one is positive or negative, the blue and the brown wires are the ones that the blue wire, the neutral, just acts as the zero. So thinking about our graph a minute ago, there it is, and then the live wire is positive, then it's negative, then it's positive, then it's negative, then it's positive, then it's negative, and the neutral wire stays here. So you've got live and neutral. The earth wire usually isn't used. The earth wire is only the yellow and green stripy one. It's only ever used if there's a fault in the appliance. And then what it does is it takes the electricity down through the wire into the ground underneath your house, and as it does that, it breaks the fuse. That means you're protected from an electric shock. So the earth wire is just a safety wire. Usually only objects that have a metal case, or a metal object where you can touch it, like a toaster or something, that would have an earth wire. A kettle would have an earth wire. Some things like a radio or a stereo that's made of plastic and you can't touch the metal inside does not have an earth wire. So this top box here just explains all of that. The live wire is the dangerous one. That's where you could get electrocuted, and the earth can cause the electricity to flow into the ground and therefore break the fuse. So that pretty much says what we just said a minute ago. Back to the equations. Power. Well, it's gone past the power equation and I can't go back. So what I'll do is, that's better. The power equation, power is volts times amps. So potential difference times current. Voltage in volts, and I, the current, in amps, and power is measured in a unit called a watt, symbol capital W. Make sure you're changing kilowatts or anything else into watts. Different power equation. Power is current squared times resistance. Different way of working it out. Remember, you've got the equation sheet. They will give you figures if they give you the resistance, and if they give you the current, you know to use this equation. Whereas if they gave you volt, potential difference, and current, you use that equation. They might give you the information to work out the resistance for this first one, and then you use the resistance. In last week's revision you did energy, so energy transfers, some of the common ones in the motor, changing electrical energy to kinetic, a light bulb changing electrical to light, and a heater changing electrical into heat. And just remembering, the energy efficiency is how much is useful, and the more efficient it is, the less that will be wasted. I'm going to try not to flick past this equation straight away. Energy in an equation is power times time. So from a point of view that power is how quickly we use energy, so for example, if something was 500 watts, what that means is it's using 500 joules per second. So to work out the energy, here we have the watts, which is how much is used per second, and you times it by the number of seconds, and then you know how much energy is being used overall. The units, if you're not sure of, are in the table there as well. So for example, they give you a question. I'll go back to highlighter because I'm good like that. An electric motor with a power rating of 5 kilowatts. As soon as I see kilowatts, I'm thinking to myself, ooh, 5,000 kilowatts? That is 5,000 watts. Work out the energy transferred. So I know from my equation sheet, I go for energy is power times time. 5,000 watts. 2 minutes? No, not 2 minutes. 2 times 60 is 120 seconds down here. There. And then I'll stick it in my calculator. Similar. A different electric motor has a rating of 8 kilowatts. So again, I'm straight to thinking 8 kilowatts, 8,000 watts. This time they want to get the charge flow, so they're trying to do 2 equations. It makes it difficult to answer. However, what they've done here, on the first section, where they've given you 1.5 minutes, easy to convert to 90 seconds, easy to convert your 8 kilowatts to 8,000 watts, and you can work out energy. So energy here, because they've given me the power and the time, I can work out the energy, 720,000 joules, and charge flow is energy, coulombs, the charge, and voltage. They've given me the voltage here. So there's my 230 volts. There's my energy from my first equation, and therefore just divide them and you get the answer. Last couple of bits. The national grid. The national grid is how we send all the electrical power from power stations all around the country. A step-up transformer increases the potential difference. Look here, as in not look here, but if you look there, it's sent around the country at 132,000 volts. Because we send it round at high voltage, you get less resistance. When it gets near factories, homes, etc., the electricity goes through a step-down transformer, so it's gradually stepped down until it's 240 volts to your home. Now you might think, why does he say 240? Earlier he said 230. So our electricity is generated at 230, but all the appliances we use and everything else says 240. It's a bit of a safety margin. So we tried to send electricity at 230, but all of the appliances can handle 240. So there's a bit of a safety margin there so that things don't break so often. And last slide, why do we use transformers? If you remember the equation, power equals volts times current. Because we send it at a really high voltage around the country, we can send it at a low current, and the lower the current, the less electricity is wasted. Okay, that's the end for this one. Thank you.